In this video, I want to show you a demonstration that I used in class to demonstrate the sampling distribution of the sample proportion and some of its properties. First, I divided students into pairs and gave each pair 10 dice. Then, one member of each pair rolled all 10 dice, and the second member recorded the 10 numbers that were rolled. That was repeated 10 times until each pair of students had 10 columns of numbers, 10 samples, with 10 numbers in each column. Then, for each column of 10 numbers, students circled and counted the number of values that were 4 or greater. Then they computed the sample proportion for each of the 10 samples, so each pair had 10 samples. So it might look like this. In fact, this case I have it the other way. 10 rows. Each one of those rows is one sample. So the first sample was, you roll the dice, and one of them had a 3, one of them had a 2, one of them had a 4, and so on. Then I asked them to circle all the numbers that were 4 or more. For each one of those, compute the sample proportion. So in the first sample, there were 6 numbers that were 4 or greater. That's a sample proportion of 6 out of 10, or 0.6. So here's what it would look like for one student. Note that the sample proportion is not the same for each samples. There is sampling error. That is, one time you take a sample, you'll get this, another time that. It's just like if you flipped a coin 10 times. Sometimes you would get 5 out of 10, sometimes 4 out of 10, sometimes 7 out of 10. It's going to vary sample to sample, and that's called sampling error. And when we measure that in future problems, we're going to call that standard error, which is kind of like standard deviation, but it's the sampling error in a sampling distribution where now the random variable is the sample proportion itself. Then the groups all came up and plotted their sample proportions on the board. Unfortunately, I didn't take a picture of it. This is one where they computed sample means, actually. But it kind of looked on the board something like this, except for it was p hats instead of x bars. The main thing to notice about this graph is its shape. It's a bell curve. Here's one that I just drew on my own, just to show you what the symbols are and how it fits in. Of course, this isn't as many proportions as the students in the class drew on the board, but what I do want you to notice is that each one of these p hats represents one sample. So when they had 10 samples, they might put one p hat as 0.6, another one as 0.4, and another as 0.3, and just keep stacking them up. After the class did that, it did have this bell shape to it. Let me stress, again, that each one of these is one sample proportion, but then when we look at all of these together, we're going to be talking about the sampling distribution of the p bars. It's that fact that this sampling distribution of p-bars is a bell curve that allows us to use the z-table and other related tables and distributions as we move forward in the class to test hypotheses, compute p-values, and construct confidence intervals. I know you probably don't know what those are yet, but that's what we're going to be doing for the rest of the course.